An equation of the form f of x equals 0 can have no solution, one solution, or many solutions. In numerical methods, the solution of f of x equal to 0 can be divided into two groups, the bracketing methods and the open methods. In bracketing methods, within a given interval ab, f of x should be continuous and has a solution. In this given interval ab, the true solution should be bracketed by this interval, such that the interval ab becomes smaller and smaller and gets nearer to the true solution of the function f of x. One of the bracketing methods is the false position method. In this method, the solution starts within a given interval a sub 1, b sub 1, and then the points on the graph at x equals a sub 1 and b sub 1 is connected by a straight line. Notice that this straight line touches the x-axis. This point wherein this straight line touches the x-axis will be the first estimate of the root, which will be denoted as x sub r1. Then, this value is then projected to the graph of the plot of the function, and we have our second subinterval, which our a sub 1, our x sub r1 becomes a sub 2. Connecting again those two lines, those 2 points by a straight line, and it touches again the x-axis. That point wherein the straight line touches the x-axis becomes our second estimate of the root. Continuing the process, as our process continues, the approximate root gets nearer and nearer to the true solution of the function. From the figure, using similar triangles, we know that this distance here is equal to x sub r1 minus a sub 1. And this distance here is b sub 1 minus x sub r1. By using similar triangles, we get this equation. The function at x equals a sub 1 all over this distance here is equal to the value of this distance here, which is equivalent to the value of the function at x equals b sub 1 divided by the distance here. So algebraically manipulating this equation, we get the value of x sub r1, which is equal to this expression, which can be generally indexed as x sub ri is equal to this expression here. This will be our equation 4.3 from our module provided. So the algorithm of the false position method is this. First, again, we choose the first interval AB. We choose the first interval AB such that a solution exists between them. This can be checked using or by multiplying the function at x equals a and x equals b such that the product of these values of the function should be negative or less than 0. Next is to calculate the first estimate of the root using equation 4.3. And again, by making these evaluations such that f of a sub I multiplied to the first estimate or the ith estimate of the root, if that is negative, the true root lies between these values of x. And setting this b sub I plus 1 to x sub r I, and again returning it to step 2. The termination criteria is still the same with the bisection method. You have the true error and the approximate percent relative error, such that you terminate your algorithm or you terminate your process when a stopping criterion is achieved. So as an example of the false position method, we will use the example in bisection method, which was the example 4.1. So again, we will create table that displays the values of a, b, x, r, and other parameters included. And the approximate error for each iteration should also be displayed. Use again the stopping criterion 0.5%. So since we know the location of the root to be at the interval 2, 3, we have our a sub 1 equals 2 and b sub 1 equals 3. So at first iteration with I is equal to 1, our a sub 1 is equal to 2 and b sub 1 is equal to 3. The functions of x, the values of the function at x equals a sub 1 and b sub 1 should be calculated. So here are our values. So our first estimate of the root is 2.38858. And the value of the product of these function values is positive or greater than 0. Therefore, we set our a sub I plus 1 to a2, and that will be, which is equal to our x sub r1, and retain the value of b. Continuing the process until the value of the approximate percent relative error is less than the specified termination criterion or the stopping criterion, we get these values. Notice that at third iteration, our approximate root, the value of the approximate relative error is at 0.122, which is less than the specified stopping criterion, which is 0.5%. Remember that in using the bisection method, we stopped at iteration, I think, at iteration 7. It reached the stopping criterion or the percent relative error, which is less than 0.5%. But in the false position method, we reached that stopping criterion only at the third iteration. Also notice that at 7th iteration to 10th iteration, the values of our approximate root repeats and repeats. If this is the case, then our algorithm reaches what we call convergence.